Hello, Professor. My name is Liu Yu, and my teammates is Zhang Hengmin and Chen Yang. Okay, let's begin with the introduction to the dataset we are working with. Okay, the title is AZ's News Topic Classification Dataset, and the source for the source dataset was collected by the Come2My an academic news search engine. It consists of over 1 million news articles gathered from more than 2,000 news sources over a year, and it's widely used for research in text mining, classification, clustering, information retrieval, and other non-commercial purposes. The full datasheet is split into 120,000 training samples and 7,600 testing samples, and it has 4 distinct news categories: world, sports, business, science, or technology. Its news article in dataset has 3 key columns: class index, title, and description. Then I will introduce the text processing and data preparation. In this section, we will discuss how the data is prepared for the model. Below are the key pre-processing steps applied to the AZ News topic classification dataset. First is lowercase conversion. To maintain uniformity, all text data is converted to lowercase. This step ensures that words like apple and apple are treated as identical, preventing any unnecessary differentiation. Then is remove URLs and HTML tags. Then is remove non-alphabetic characters. Non-alphabetic characters such as numbers, punctuation marks, and special symbols are removed from the text. This step ensures that only meaningful words are retained under classification. For the step words are common words like the and is that carry a little to the no significance in the context of the text classification. Using the NLTK stop words list, we filter those out to reduce noise in the data set. Stemming is applied to reduce words to their base form. For example, the word running, runner, and run are all reduced to the root word run using Porter-Stemmer algorithm. Then is for the data preparation. For data input, we combine the title and the description columns into a single text column for both the training and data sets. This step ensures that the model has access to entire content of the articles. Then also we tokenize the text, meaning that each word in the article was converted into an integer sequence using a fixed vocabulary size of 10,000 words. This process allows the model to work with the numerical representation of the task. To handle sequence of varying lengths, we apply padding to ensure that all text sequences have the same length of 177 words. Based on the dataset's average text length, padding helps the model process data consistently, improving efficiency. And here is the brief visualization of the news data. Highlight category distribution and key term extraction. The pie chart indicates that the dataset is balanced with 4 categories: words, science or technology, sports, and business. It's comprising 25%. The word cloud of all titles reveal frequent terms such as router, Reuters, AP, and C, reflecting its topic and new agencies. The business news word cloud emphasizes the term like oil price, stock, and market, indicating a focus on financial topics. Meanwhile, the most frequent word in the sports news include win, game, and team, showing a strong emphasis on match results and competition. Let's now look at the architecture of the RNN model that we built for the task. The model follows the standard structure designed for text classification, and it includes several layers aimed at capturing both short and long-term dependencies in the text. We start with an embedding layer to convert the integer encoded vocabulary into dense vectors of the fixed size. This helps the model better understand the relationship between words. We use two bidirectional sample RNN layers. The first has 128 units and the second has 64 units. The bidirectional aspect allows the model to capture both past and future context in the sequence of the word, which is particularly useful in the text classification task. After processing the sequence through the RNN layer, we apply global max pooling 1D. This operation reduces the sequence of the word to a fixed length representation by selecting the maximum value for each feature across the sequence. We then have three fully connected layers with 256, 128, and 64 units. These layers are followed by dropped-out layer to help prevent overfitting by randomly setting a fraction of input unit to 0 during training. Finally, the output layer uses softmax activation function, which is ideal for multi-class classification. It outputs a probability of each of the four categories, and the class with the highest probability is chosen as the predicted label. Now let's review the evolution results of our model. The model achieved accuracy of 90.22% on the validation side, indicating strong performance in classifying news articles. Precision and recall are both around 90%, meaning the model does a great job of both identifying relevant classes and correctly classifying all relevant examples. The F1 score, which is harmonic meaning of the precision and recall, is also 90.18%, demonstrating a balanced performance in both metrics. And here we have a confusion matrix that shows how well the model performed in each class. For example, the model correctly classified 1709 articles from class 0 out of 1900 total samples. The accuracy curve also shows a steady increase in both training and validation side, with a slight fluctuation which is expected as the model learns. The loss curve indicates that the model is converging with the training loss decreasing significantly, and the validation loss is similar trend. This result demonstrates that the model is performing well, but there is still room for improvement, especially in reducing misclassification between the certain classes. Then is the CNN model. For the architecture, the input data set expected by the CNN is usually a 3D tensor. It's necessary to add a channel dimension to become bunch size, which is 64 and 1 and 5000. The final output layer, assuming there are 4 categories, so the output dimension is 4. The first conventional layer, for the first conventional layer, the number of input channel is 1 and the output channel is 128. The conventional kernel size is 3. And the conventional, there is also activation function and maximum pooling layer for the convolutional layer to reduce the size of the features and improve the model calculation efficiency. For the second convolutional layer, number of input is 128. The number of output channel is 256, which has deeper picture extraction. And the convolutional kernel size is 3. After convolutional and pooling, the output flattens into a one-dimensional vector. This part is fully connected layer. And under dimensional 256 multiplied by 1248, and the output dimensional is 128, and the dropout is used to prevent overfitting. And finally, output is 4, which represent the 4 categories. And here is the training validation curves. The accuracy curves of both training site and validation sites shows a steady upward trend, indicating that the model gradually improved its classification ability during the learning process. The training loss decreased from 0.4370 to 0.1700. And the validation loss decreased from 0.3149 to 0.2952, indicating that the model gradually converged on both training and validation sites. A slight increase in the loss of validation in round 5 may indicate that the model is starting to overfit. And for the evolution matrix, the model has an accuracy of 94.16% on the validation side, indicating that the model is very good at classifying news articles. Precision and recall both have values around 93%, indicating that the model is doing a good job of identifying relevant categories and correctly classifying all relevant samples. For F1 score, the F1 score is harmonized the average of precision and recall with a value of 93.25%, indicating that the model performs evenly on those 2 metrics. The confusion metric shows how the model performs on each category. For example, the model correctly classified 930 articles from category 0 with a total sample size of 1000. The classification effect of category 3 is slightly worse, and 860 articles are correctly classified, indicating that the model has some misclassification on category 3. Now let's move to the LSTM model. It has an embedding layer, LSTM layer, and a fully connected layer, and it's all approximately 9.3 million parameters primarily concentrated in the embedding layer. And early stopping is applied to prevent overfitting by monitor validation loss. It can prevent overfitting, speed up training, restore best width. And for the result, the highest F1 score is 0.96, and the highest precision is 0.95 with a recall of 98%. And for the words, the precision is 0.93, but slightly lower recall 0.9, and the F1 score is 0.91. Business and science technology have the lowest score, means that the model is not good enough, so we tried the BI-LSTM model. BI-LSTM model, we add dropout. This is regularization technique. used to prevent overfitting in neural networks. It works by randomly deactivating a fraction of neural during training, forcing the model to learn more robust features. We cite the dropout rate at 0.25. For the results, sports the highest score F1 highest F1 score at 0.96 with a recall of 98%, indicating that the model really misses the relevant cases. For the word category, the second highest precision with 0.94, but slightly lower recall, which is 0.87, suggesting a few missed instances. The main classification were business and science technique, likely due to the topic overlap. Business and science technique category both have an F1 score of 0.88, indicating room for improvement. The confusion matrix business and science technique is quite obvious. By category, figures shown below show the summary of performance of all the models we use in the project. From the graph, we can see that CN, LSTM, and BLSTM are the top three models in terms of the performance, with accuracy of 0.91 on test site. If you prefer to predict one, you can choose BLSTM model. If you prefer to predict 4, you can choose LSTM model or CN model. Okay, that's all. Thank you for listening.